All right, so we're going to start section 3 of chapter 3. Talking about zeros of polynomials and functions. All right, so the first thing that we need to go over is the factor theorem and what the factor theorem states. So the factor theorem says that for f of x, x minus k is a factor of the polynomial if and only if f of k is equal to 0. All right, so as we're copying that down, remember that with the remainder theorem states that if x minus k is a factor, or excuse me, if x minus k is used through synthetic division, then the remainder of that synthetic division is f of k. So if we combine the remainder theorem and the factor theorem, it's basically stating that if we're given x minus k, we can see that this is a factor. If we run it through our synthetic division, and the remainder ends up being 0. All right. So if it's a 0, which means our remainder of the synthetic division is a 0, then x minus that value k is a factor as well. So we can tell a lot from the remainder of our synthetic division. And we're going to use the factor theorem to test if what we're given is a factor of the given polynomial. So our first example, we're asked, is x plus 4 a factor of the function f of x? Which is the polynomial, I'll put it down here, 3x to the 4th minus 48x squared plus 8x plus 32. All right. So once again, we're trying to see if the factor is x plus 4 a factor of the polynomial, 3x to the 4th minus 48x squared plus 8x plus 2. All right. So the way we're going to test this is by setting up our synthetic division. Remember that when we're setting up our synthetic division, we take the opposite of what we see. So here we're given positive 4 as a factor, or we're trying to see if it is a factor. So we're going to put negative 4 in our synthetic division. And we're going to list our coefficients, making sure that we account for every degree of x. So here we're starting with x to the 4th, and then we jump straight to x squared. We have to plug in a 0 for that x cubed column. So our coefficients will be 3 for our x to the 4th column, 0 for the x cubed, negative 48 for our x squared, 8 for our x's, and 32 will represent our column, our constant column. Remember, in order for x plus 4 to be a factor, then we must get a remainder of 0 in our synthetic division, running our synthetic division through the value of negative 4. So we're going to bring down our first value. Our 3 plus 0 gives me 3. Adding vertically, multiplying diagonally. 3 times negative 4 will give me negative 12. 0 plus a negative 12 will give me negative 12. Negative 12 times negative 4 will give me a positive 48. Negative 48 plus 48 will give me 0. 0 times negative 4 will give me 0. 8 plus 0 will give me 8. 8 times negative 4 will give me negative 32. And positive 32 plus a negative 32 will give me a remainder of 0. So the fact that we got a remainder of 0 through our synthetic division, that lets us know that x plus 4 is a factor of the polynomial 3x to the fourth minus 48x squared plus 8x plus 32. All right, any questions on that first example? All right, so once again, if we get a remainder of 0 in our synthetic division, x minus the number that we ran through our synthetic division, or the opposite of what we see, will be a factor of the polynomial. So another one like it, if we were given, or we're asked to find is x plus 4 a factor of f of x, and this time our f of x is x to the fifth plus 6x to the fourth plus 11x cubed plus 12x squared plus 5x minus 20. Sorry about that. I thought I had no space to do it. And we're still trying to see, is x plus 4 a factor of that given polynomial? Once again, we're just going to test that using our synthetic division with the understanding that if we run our synthetic division and we get a remainder of 0, then x plus 4 is a factor of the given polynomial. All right, so we're going to set up our synthetic division. Put our -4 outside our bracket. We're going to make sure that we're accounting for every degree. This time we're starting with x to the fifth, x to the fourth, x cubed, x squared, x to the first, and constant. Constant is -20. So we don't have any missing degrees. So we can just list our coefficients, which will be 1, 6, 11, 12, 5, and -20. We're going to work through it just like we did in our previous problem. So I'm going to bring down our 1 first. Our 1 plus 0 is 1. 1 times -4 gives me -4. 6 plus a -4 gives me +2. 2 times -4 will give me -8. 11 plus a -8 will give me a +3. 3 times -4 will give me -12. +12 plus a -12 will give me 0. 0 times -4 will give me 0. 5 plus 0 will give me 5. 5 times -4 will give me a -20. And -20 plus a -20 will give me a -40. So this time, when we run that -4 through our synthetic division, we get a remainder of something that is not 0. And as long as we get something that is not 0 as our remainder, then we know that what we're running, or the number that we're testing, is not a 0 of the polynomial, which means that x plus 4 would not be a factor of the polynomial. Any questions on this one? So with that understanding, we know that if we're given, we find a 0 of the polynomial, remember the 0 is just another way of us saying that the number that we're running through our synthetic division has a remainder of 0. If it gives us anything other than 0, it's not a 0 of the polynomial. But if we have a 0, then we know what a factor is as well. All right? So that means we can do some factoring given a 0. An example of this, if we're given the function f of x, which is 6x cubed minus 37x squared, plus 32x plus 15. We're trying to see if 5 is a 0 of the polynomial. Keeping in mind that if 5 is a 0, x minus 5 is a factor. Now, also recognize the fact that we're starting with x cubed. So if 5 is a 0, then our answer starts off with x squared or quadratic. So we can take advantage of our calculator, use the quadratic formula, or we can do it by hand. It makes no difference to me. If it were me, I would tell you to lean on the calculator. Make sure that you know how to do it efficiently, because that's much quicker and there's a lot less opportunity to make a mistake. All right, so we're going to set up our synthetic division. Here we're trying to see if 5 is a 0. So we're going to set up our synthetic division. 5 on the outside. Notice this time we're just using 5, not the opposite of what we see, because they did not show us a factor. Making sure that we're accounting for every degree, starting with x cubed, x squared, x 15. So we have no missing degrees. So we can list our coefficients: 6, negative 37, 32, and 15. All right, so we can bring down our first one. Our 6 plus 0 gives me 6. 6 times 5 will give me 30. Negative 37 plus 30 will give me a negative 7. Negative 7 times 5 will give me a negative 35. 32 plus a negative 35 will give me a negative 3. Negative 3 times 5 will give me a negative 15. And positive 15 plus a negative 15 will give me 0. So that lets me know that 5 is a 0, which in turn tells me that x minus 5 is a factor. Which means that this 6 minus 7 minus 3 represents the polynomial 6x squared minus 7x minus 3. That's what we'll have to multiply x minus 5 by to get back to our original polynomial f of x. All right, so at this point, we can recognize we have our factor x minus 5, and we can multiply by our quotient, which we just found to be 6x squared minus 7x minus 3. Now to solve this, we can use our quadratic formula. But like I said before, I would suggest using the calculator, plugging in A for 6, or 6 for A, negative 7 for B, and negative 3 for C, and allowing the calculator to do the work for you. And the solutions you should get when using the quadratic formula, keep in mind you could do this by hand if you desire to do so. Positive 3/2 and negative 1/3 will be the solutions that we'll get by using that quadratic formula. All right, so this actually can be factored further. This is when you want to think back to our factoring techniques. Remember in chapter 1, we could factor this quadratic, or excuse me, we could factor this trinomial with a leading coefficient other than 1. The easiest way to do it though is to recognize that we just found positive 5 to be a 0. If these are the solutions to the quadratic formula here, then 3/2 is also a 0, and negative 1/3 is also a 0. Remember, if we have zeros, then we know what our factors are. It's simply x minus that 0. So another 0 that we will have, or another factor that we will have, will be x minus 3/2 and x plus 1/3. Now, so remember that if we're given the zeros, we write the opposite of what we see in a factor, and vice versa. If we're given the factor, we write the opposite of what we see as a 0. Now, obviously, we're not used to seeing fractions, or we don't have fractions in the completely factor form. The easiest way to get rid of a fraction, multiply by the denominator. So the completely factor form of this particular quadratic, or of this particular polynomial, would be x minus 5, 2x minus 3, multiplying both the x and that 3/2 by the denominator of 2, and 3x plus 1, multiplying both the x and the 1/3 by the denominator of 3. All right. And that would be the completely factor form using our synthetic division along with the remainder in the factor terms. All right. Any questions on this? We have another thing that we can go over, which is called the rational zeros theorem. The rational zeros theorem is just a way for us to find a list of zeros that could possibly be zeros if we're given a polynomial, but we can always check it through our synthetic division. So our rational zeros theorem rational zeros theorem states that if P over Q is a possible zero, then P represents the factor of the constant. And Q represents the factors of the leading coefficient. Making sure that we're accounting for the positive and the negatives of each and every one of those integers. An example of this, we're given the function f of x, which is equal to 8x to the 4 minus 26x cubed minus 27x squared plus 11x plus 4. And we're asked to use the rational zeros theorem, which in turn gives us a list of possible rational zeros. All right, so I'm just going to abbreviate this. PRZ represents the possible rational zeros. Keep in mind that this list is going to include a lot of numbers. All of them will not be zeros of the polynomial. The way that we're going to test it is either by using synthetic division or a quadratic formula, depending on what the degree is of the polynomial given. All right, so here, the way we're going to find that list, we're going to put a list of factors of P over Q. Keeping in mind that P represents the factors of the constant, or in this case, my constant is positive 4. The factors of 4 are the numbers that we can multiply to give me 4. 1, 2, and 4. And the factors of Q are the factors of the leading coefficient. In this case, my leading coefficient is 8. The factors of 8 is 1, 2, 4, and 8. Now, what we're supposed to do is take the factors of P, put them over the factors of Q, accounting for the positives and the negative combinations of each and every one of those integers. All right, so our factors of P, 1, 2, and 4, need to be over each and every one of these factors of Q. Keeping in mind that if it repeats or if it reduces down to a 0 that we already accounted for, there's no need for us to write it again. So the way that I think of it, anything over 1 is itself. So just to be clear, I'm putting both 1, 2, and 4 over each and every one of these integers. So 1 over 1 gives me 1. So one possible 0 is both positive and negative 1. 2 over 1 is 2. So one of our possible zeros is both positive and negative 2. 4 over 1 is 4. So another possible 0 is both positive and negative 4. So we place 1, 2, and 4 over 1 as a denominator. We'll do the same thing for 2. 1 over 2 gives me both positive and negative 1/2 as a possible 0. 2 over 2 reduces down to 1. We've already accounted for both positive and negative 1. No need for us to write it again. And 4 over 2 reduces down to 2. We've already accounted for both positive and negative 2. No need for us to write it again. Now we're just going to continue that same process, placing 1, 2, and 4 over 4. 1 over 4 gives me both positive and negative 1/4 as a possible 0. 2 over 4 reduces down to 1/2. We've already accounted for both positive and negative 1/2. And 4 over 4 reduces down to 1. We've already accounted for both positive and negative 1. And the last one is to place 1, 2, and 4 over the denominator of 8. So we have 1 over 8 are positive and negative 1/8 is a possible 0. 2 over 8 reduces down to 1/4. We've already accounted for both positive and negative 1/4. 4 over 8 reduces down to 1/2. We've already accounted for both positive and negative 1/2. So our list of possible rational zeros is 1, 2, 4, 1/2, 1/4, and 1/8, being both the positive and the negative representation of each of those numbers. So we have 1, 2, 3, 4, 5, 6, or a total of 12 possible rational zeros. All right. Is anybody has a question? Is there anybody who does not see all 12 possible rational zeros in this particular example? Are there any questions on how we ended up getting 1, 2, 4, 1/2, 1/4, and 1/8, both the positive and the negatives of each of those possible rational zeros? Now, in order for us to find, these are the list of possible zeros, which kind of cuts down on all the integers that we could test. But to find the zeros, we can use the calculator and then prove with synthetic division. All right, so take a note that to find the zeros, we can get it from our calculator. And then we can also prove it using our synthetic division. Depending on the calculator you have, especially if you have the Casio, that's why I prefer the Casio. You can actually just plug in these quadratics, or excuse me, not necessarily quadratic, but these polynomials all the way up to like degree 6. So a problem like this one, where it starts all the way up, or the highest possible degree of x instead of 4, we can plug that into our calculator and check it. But whether we have the calculator to do it or not, we can always check it using our possible zeros or in our synthetic division. So just continuing. Trying to see if x is equal to -1 and +4, trying to see if these are zeros for the polynomial, which in turn tells us the factors. All right. Now, if we have 2 zeros, this breaks this down, this original polynomial down, all the way down to x squared. Keeping in mind that every quotient is 1 degree less than our dividend. So at that point, we can use the quadratic formula or our calculator. So testing -1. My coefficients will be 8, -26, -27, 11, and 4. Bring down our 8. 8 times -1 will give me -8. -26 minus 8 will give me -34. -34 times -1 will give me a +34. -27 plus 34 will give me a +7. 7 times -1 will give me a -7. 11 plus a -7 will give me a +4. 4 times -1 will give me a -4, which in turn gives me a remainder of 0. So this lets me know that -1 is a 0 polynomial, or x plus 1 is a factor. Now, because this has a remainder of 0, we can actually continue using this quotient and test the +4. Now, we can only do that if the remainder is 0. So if it is not 0, then we have to just continue using the original coefficients in our original f of x to see or test the next value. For the sake of time, we're just going to pretend like I already tried +1, it didn't work. -1 just worked. +2 and -2 didn't work. So getting this from our possible zeros. +4 also didn't work. So the next one I'm going to test is actually, well, I'm sorry, -4 didn't work. The next one I'm going to test is +4. So we can set it up, putting our +4 on the outside. And because we have a remainder of 0, we can continue using our synthetic division to see if this is a 0 of the polynomial, which in turn will tell us if x plus 4, or excuse me, x minus 4 is a factor. So once again, we can bring down our 8. 8 times 4 will give me 32. -34 plus 32 will give me -2. -2 times 4 will give me a -8. +7 plus a -8 will give me -1. -1 times 4 will give me a -4. And once again, we end up with a remainder of 0 because +4 plus a -4 gives me 0. All right. So at this point, now we have 2 zeros of the polynomial, one being -1, the other being +4. So we know x plus 1 is a factor. X minus 4, also a factor. And this would be multiplied by 8x squared minus 2x minus 1. Now we got that 8x squared minus 2x minus 1 from our quotient, or our answer from that second synthetic division. Now we can continue working our possible rational zeros all the way out to positive and negative 1/8. But at this point, it's a quadratic, so there's absolutely no reason why we couldn't use a quadratic formula to get the last two zeros, either the calculator or by hand, or if we could factor it. Because remember, we have a few techniques to solve quadratics. Now, technically, this is provided that you're good at factoring. Factoring is the quickest way. So just to show you that this also works here, we can factor this 8x squared minus 2x minus 1. Remember, if we're factoring a trinomial with a leading coefficient of something other than 1, we can use the AC method. We'll multiply our 8 and our 1, the first and our last, and rewrite it as a problem that we're used to factoring. So in this case, it would be x squared minus 2x minus 8. We can factor that, keeping in mind, first we multiply by 8. So once we get our answers, we need to go back and divide by 8. So we're looking for two numbers that we can multiply. They'll give me negative 8 that we can combine to get negative 2. And those values are 2 and 4. In order for the 2 to be negative, the 4 must be negative, the 2 must be positive. Now, this is when we want to remember that we multiply by 8 at the beginning, so we need to go back and divide by 8 to simplify. So this will be x minus 1/2 x plus 1/4. At this point, we really want to pay attention to what's being asked. This one, remember, we're asked to find the zeros for of this given polynomial. So our list of zeros, out of the list of possible rational zeros, will be negative 1, positive 4, from our synthetic division, as well as positive 1/2 and negative 1/4. What we just got from our factors. Remember, we're given a factor, take the opposite of what we see for our list of zeros. Any questions on this one? All right, the last type of problems you're going to see, the last types of problems that we're going to see, we have a few examples for this one. This is where we're given zeros and we're asked to write an equation to match it. So it's kind of like we're working backwards. At this point, we're given f of x as our polynomials, and asked to find the zeros or the factors. Keeping in mind that factors are tied to zeros. This time, we're going to be given zeros or factors, and we're going to be asked to write the polynomial function. All right, so here, we're asked to write the equation. In our first example, we're told that it's an equation of degree 3, which means the highest degree of x will be x cubed. And we're told that our zeros are negative 3, negative 2, and 5. We're also told that f of negative 1 is going to be equal to 6. All right, so like I said, this time we're given a list of zeros as well as a general statement. Typically, if they give us a general statement like here, where f of negative 1 is equal to 6, we're going to use that general statement to find the leading coefficient in the completely factored form. All right, and I'll show you what that means a little more. But first, we're going to use our list of zeros to write out our factors and start multiplication. So remember, we're looking for our f of x, our given polynomial. And if we're told that our zeros are negative 3, negative 2, and 5, that means that our factors will be x plus 3, x plus 2, and x minus 5. All right, so remember that if they give us zeros, we take the opposite of what we see, put an x in front of it, and that's going to be a factor. All right, so at this point, we can start multiplying. If it were me, I would go ahead and FOIL out x plus 3 times x plus 2. We know x times x gives me x squared. X times 2 give me 2x, plus 3 times x, which gives me 3x, 2x plus 3x. It's going to give me 5x, plus 3 times 2 will give me 6. We still need to multiply this by x minus 5. Now, so I've just multiplied, FOILed out my first two factors. Now what I need to do is take this trinomial, x squared plus 5x plus 6, and multiply by the binomial, x minus 5. Now, one way that I always do this, when it's a binomial and a binomial, we have the FOIL technique. I always like to think of it, whenever we're multiplying a trinomial and a binomial, I'm just distributing every element in my binomial. So just to be clear, I'm going to multiply x squared plus 5x plus 6 by x. Then I'm going to multiply x squared plus 5x plus 6 by negative 5. After that, I'm going to combine my like terms. All right, so multiplying everything by x, it's going to give me x squared times x gives me x cubed. 5x times x gives me a positive 5x squared. And 6 times x gives me a positive 6x. Now I'm going to multiply everything by negative 5. Negative 5 times x squared gives me a negative 5x squared. Negative 5 times a positive 5x gives me a negative 25x. And negative 5 times positive 6 gives me a negative 30. And now what I need to do is go through and combine my like terms. My x cubed, does it have any like terms? That's going to be a part of my answer. I have 5x squared, negative 5x squared. Those are going to cancel out. Positive 6x, negative 25x. Combine those like terms, that's going to give me a negative 19x. And negative 30 is a part of my answer because I don't have any like terms to combine it. So that's a polynomial of degree 3 that matches the zeros, negative 3, negative 2, and 5. Now, like I said before, we're still going to use the fact that f of negative 1 is equal to 6. That's how we're going to find that leading coefficient or a factor that we're going to pull out and put out front. So part of our answer is this x cubed minus 19x minus 30. But this one we want to recognize that f of negative 1 would be equal to 6, which is going to equal to some a. That's that leading coefficient or that factor out front. That's what we're looking for. And we're going to use a completely factored version, or that x plus 3 times x plus 2 times x minus 5 to figure out what a is. So remember, if f of x is x plus 3 times x plus 2 times x minus 5, f of negative 1 will be negative 1 plus 3 times negative 1 plus 2 times negative 1 minus 5. Now we're replacing every x in f of x with negative 1. All right, so that's actually going to give us enough information to figure out what those values are being multiplied, what values are multiplying by a. So this is going to be a times negative 1 plus 3 will give me a positive 2. Negative 1 plus 2 will give me a positive 1. And negative 1 minus 5 will give me a negative 6. Keep in mind, this is still equal to that 6, or 6 is equal to a times negative 12, which is what we get as a product from 2 times 1 times negative 6. Now to solve for a, all we have to do is divide both sides by negative 12. And we can see that a is equal to negative 1/2. All right. So the function that we're looking for, f of x that is degree 3, that satisfies all those given conditions, will be negative 1/2, that a, or a factor, being multiplied by x cubed minus 19x minus 30. And that would be our final answer. Any questions on that one? All right, so just pay attention to the fact that if they start the problem off and they tell us f of some value is equal to a number, that's what we're going to use to find that coefficient a, or that factor that's pulled down our front. Outside of that, just remember that they give us a list of zeros. They basically have told us the factors that we need to multiply to get that polynomial f of x. All right, another problem like it. This time we're told that we're looking for a polynomial of degree 3. And we're told that 4 is a 0 of multiplicity 3. We're also told that f of 2 is equal to negative 24. All right. So we know it should be degree 3, so highest power of x should be x cubed. We're also told that 4 is a 0 of multiplicity 3. Now it says when it starts speaking on multiplicities, that just simply means that that's how many times the factor is being multiplied times itself. So when it says 4 is a 0 of multiplicity 3, they're basically telling us that x minus 4 is a factor. And we must multiply that factor by itself 3 times. So working on f of x, we know x minus 4 is a factor, that 4 is a 0, and it's multiplicity 3. So we need to multiply it times itself 3 times. Right? Now we could tell in the last problem that when they told us that f of 2 is equal to negative 24, we're going to use the complete factor conversion to figure out what that leading coefficient or that factor a is. So we're going to go ahead and jump to that one first. So we know that f of 2 is equal to negative 24. In this case, that would be equal to the a that we're looking for times times 2 minus 4, or negative 2 minus 4. I'm sorry, it said f of 2, so that's positive 2 minus 4 times positive 2 minus 4 times positive 2 minus 4. Or we're replacing every x in f of x with 2, because this is our input now. Right? We know 2 minus 4 gives me negative 2. Negative 2 times negative 2 times negative 2 will give me negative 8. So now we have negative 24 is equal to 8 times negative 8. We can divide both sides by negative 8, and we can see that 3 is equal to 8. Right? The last thing we need to do is to simply multiply x minus 4 times x minus 4, forward that out, and then multiply that by x minus 4 to get that polynomial. All right, and for the sake of time, because I still got 2 more examples, and I know these last 2 are going to take a little more time to explain, we can see that our f of x will be equal to that a3 that we found times the polynomial x cubed minus 4x squared minus 16x plus 64. That's going to be the polynomial that we get by multiplying x minus 4 times x minus 4 times x minus 4 after we combine our like terms. All right. If you didn't even go over that, how we got that polynomial, the x cubed minus 4x squared minus 16x plus 64, just hang around at the class. I don't mind explaining it. It won't take long. It's just that we're running out of time now, and I really want to finish 3.3 with it. All right. We also have to write polynomials of a certain degree, given certain zeros, and they can be complex. By that, I mean imaginary numbers, or a plus bi. So another example, another type of problem we're going to see in this section. Here we're asked to write using complex zeros. And we want to remember the i's come in pairs. All right. So anytime they tell us a positive complex number, just understand that the conjugate is also a part of it as a complex number. And just in case anybody forgot what a conjugate is, we can go over that again in this first example. So here we're told that our zeros are -4 and 3 minus I. Now, the fact that they told us that 3 minus I is a complex number, this also lets us know that 3 plus I is another zero for this one. So if they give us one complex number, we can take the conjugate, which simply means change the sign in the middle. That's also going to be a zero for the given problem. So what we actually have to multiply is a list of factors. X plus 4, that's the factor we get from the zero of -4. X minus 3 minus I is another zero, or is another factor that comes from the zero of 3 minus I. And X minus 3 plus I is another factor that when we get from the zero of 3 plus I. Now, what we want to remember is that anytime we're dealing with complex numbers or we have i's, is that I squared is equal to -1. So we don't want to forget that I squared is equal to -1. That's going to take it from being complex and make it into real. We're also going to see, because we're dealing with conjugates, that anything else that has an I that doesn't automatically change to a real number by implementing the I squared is equal to -1 is going to cancel out. All right, so the real issue here is multiplying these two zeros, these two factors, X minus 3 minus I and X minus 3 plus I. So we're just going to show that again here, X minus 3 minus I, X minus 3 plus I. And you can just look at it as a trinomial times a trinomial. So if it were me, I'm going to multiply everything here, that X minus 3 plus I, by X, by -3, and by -I. So first by X, we have X times X, that's going to give me X squared. X times -3 gives me a -3X. X times positive I gives me a positive XI. So I multiply everything in here by X. I'm going to multiply everything in here by -3 now. -3 times X gives me another -3X. -3 times -3 gives me a positive 9. And -3 times I gives me a -3I. And now I'm going to multiply everything in here by -I. So -I times X gives me a -XI. -I times -3 gives me a positive 3I. And -I times positive I is going to give me a -I squared. Now we're just going to go through combine like terms. If it were me, that -I squared, remember I squared is -1, so this is really a -1. Or that's just going to become positive 1. We have a positive 3i, a -3i, those are going to cancel out. A -xi, a positive xi, those are also going to cancel out. We also have two more like terms, -3x and positive 3x. We can combine those like terms. That's going to give me a -6x. So what we have is x squared minus 6x. We also have this positive 9 plus 1. So it's going to be plus 10. Now it's very easy to make this simple mistake, but don't forget, we still had another factor to multiply this by, and that's that x plus 4 that's set out for. Right. So now we're just going to multiply this trinomial by x plus 4, multiplying everything in here by x, then multiplying everything in here by 4, and combining our like terms. So x times x squared, that's going to give me x cubed. X times -6x is going to give me a -6x squared. And x times positive 10 is going to give me a positive 10x. Now we'll go back and multiply everything in this trinomial by positive 4. So it's going to give me a positive 4x squared. 4 times negative 6x. It's going to give me a negative 24x. And positive 4 times positive 10 is going to give me a positive 4. When we go through and combine our like terms, the polynomial that we're left with is x cubed minus 2x squared minus 14x plus 40. This will be the polynomial of degree 3. It has the zeros, negative 4, and 3 minus I. We got one more example. This time, they can tell us to find the polynomial that satisfies the conditions, and they can just give us one possible zero or one complex zero. Is anybody who's still confident? So this time, it's going to tell us that our zeros are 2 minus I. You have to understand that this implies that 2 plus I is also a 0. So our factors, x minus 2 minus I and x minus 2 plus I. We can find a polynomial. This one is going to be a polynomial of degree 2 that satisfies this condition. But just like before, if it's a trinomial times a trinomial, what I'm going to do is simply multiply everything in the second trinomial by x, then multiply by negative 2, then multiply by negative I. So we have x times x, which is going to be x squared. X times negative 2 is going to be negative 2x. And x times a positive I is going to give me a positive xi. I'm going to multiply everything here by negative 2. So it's going to give me another negative 2 times x, or negative 2x. Negative 2 times negative 2, positive 4. And negative 2 times positive I is going to give me a negative 2i. Multiply everything here by negative I. So negative I times x is going to be negative xi. Negative I times negative 2 gives me a positive 2i. And negative I times positive I gives me a negative I squared. Once again, the easiest way to handle that negative I squared is to simply make it positive 1. That's technically a negative I. Positive 2i cancels out this negative 2i. Negative xi cancels out this positive xi. And we also have the like terms of negative 2x and negative 2x, which we can combine. So bring down an x squared, part of my answer. Negative 2x minus 2x is being negative 4x. Positive 4 plus 1 gives me a positive 5. So this is a polynomial of degree 2 that has a zeros of 2 minus I and 2 plus I. An easy way to check this is to simply use your calculator. And you can plug in A is equal to 1, B is equal to negative 4, and C is equal to 5. And our answers that it should spit out is 2 minus I and 2 plus I. All right, so these are the problems you're going to see in section 3 of chapter 3 in the homework. If you have any questions, you guys are free to go. Remember, I'm also available to help explain any of the multiplication of this problem. All right. You guys don't have any questions, you guys are free to go, and I'll see you on Monday. Keep in mind, we're on pace for our test to be next week on Friday, the last day before spring break.